All right, good afternoon. So, welcome back to Engineering 250. Yeah, that was the trippy version. All right, we got a few cameras turned on, so thank you for people who are stepping out and turning their cameras on. I appreciate the company. All right, so a lot of stuff to go over today. So first of all, let me point out an announcement I made. So I've pushed the lab dates back by about 4 days. So lab one is not due tomorrow; it's due on Tuesday. Um, and I thought Friday made sense, but it actually doesn't because what I want to do is I want to on the day that you turn in a lab, I want to be able to start talking about the next lab that day so that we've talked about it and you've had time to work on it. If I were to talk about lab 2 on Tuesday and make it due Friday, that makes no sense. So anyway, we've pushed the labs back, and going forward all the labs will be due on a Tuesday, but they're due at noon at the beginning of class, not at 5 p.m. All right, so make sure you're aware of that. And basically you'll submit the labs before class, and then once we get into class, we can talk about any questions that people had on the labs, and then after I grade them, I'll usually make some more comments in a subsequent class. So you've got a few more days for lab one. So I want to talk today about I want to continue our combination lock example and dig a little further into that. Look at how we move from truth tables to logic equations, and from there to actual circuit designs, and then eventually circuits. So we're going to keep continuing this path of starting with a problem like make a traffic light control system or combination lock. How do we eventually move towards an actual circuit that we could build? So that's my basic plan for today, and then we'll start talking more about Boolean things, representing numbers in Boolean and so on. So any questions up front before we kind of get into all of that?
I had a quick question about the function generator.
Sure.
So you mentioned something about like 50%. I don't see a setting on that.
I don't think the function generator in Tinkercad lets you change the duty cycle. But the concept, and we're not going to really need it in this class, but you'll need it in 270. The concept is, if you have a waveform, and let's just say it's just, a square wave like this. All right, so DC bias is how much we're moving it up and down, right? Frequency is how many times it oscillates per second typically. How many times does it change from up to down in 1 second? That's related to also period, which is what's the length of time from the beginning of one cycle to another. So there's a waveform with a certain frequency, and amplitude is sometimes called peak to peak voltage. It's what's the voltage difference between the high level and the low level. All right? But even with all of that, there are other waveforms we could make that have the same offset, the same frequency, and the same peak to peak voltage. And here's an example of one such waveform. Right? It still takes this long for one cycle. It still goes from here to here. It still goes from 0 up to whatever that is. But it looks different somehow, right? It's squishy. If I draw it by itself, it goes up for a little bit of time, and then it's mostly low. And then it goes up, and it's mostly low. And it goes up, and it's mostly low. Same frequency, same period, same amplitude, but a somehow different waveform. Here's yet another version. Right? Same frequency, amplitude, and so on. So the difference between these, that's what we call duty cycle. And the duty cycle is basically how long the waveform is high out of the entire period. So some function generators you can set that. The Tinkercad one you can't. But in 270 we'll actually be producing waveforms using a microcomputer, and we'll be able to control the duty cycle. And this is how some of the early Sound Blaster sound cards worked, when you could hook speakers up to a computer, which was kind of crazy at the time. They pretended that they were outputting an analog signal by doing this kind of modulation. So that's what's going on with that.
Thank you.
Yeah, you're welcome.
Sound Blaster is a name I haven't heard in years.
I know, right? It used to be like, yeah, I mean that was like the high end of computing, was you had a really good sound card, right? We didn't know about GPUs at the time. All right, anything else? All right, so let's go back.
3 minutes late. What are the questions about before?
Sorry, say again?
So I was a few minutes late and missed the first. What were they asking questions?
Oh, someone had asked a question about the function generator, and the lab talks about setting the duty cycle to 50%, and there's no setting on the Tinkercad function generator for duty cycle. So we were just talking about what duty cycle, what that means.
So what should we do? Not set it, or?
Yeah, just leave it as the default, which is 50%. All right. Well, let's play with truth tables some more, and I'm going to continue my combination lock example. So we're going to make a system with 3 inputs, and I'm going to define these differently from how we did on Tuesday, just to kind of like push the idea that there's nothing magic about these conventions. Sometimes when we push a button, we signify that with a 0. Sometimes when we push a button, we'll signify it with a 1. We can do whatever we want. This is our universe, right? So here's the convention we're going to use. A, comma, B, comma, C are going to have a logic value of 1 if that button is pushed, and a 0 if not pushed. And unlock, 1 is going to mean that the system is unlocked, and 0 is going to mean locked. And so this would be part of our system diagram, where we show the inputs and the outputs, and we explain what the meanings of the 1s and 0s are on the inputs and outputs. Okay, so system diagram. This is the top level view of a circuit, for example. And there's no detail in here about how this works. There's no gates. There's no power connections. This is basically if somebody had made this system for you, and you wanted to know, how do I use it? This is what they would give you, right? They'd give you a picture. They'd say there's 3 inputs. They're called ABC. There's an output called unlock. And here's the meaning of those, right? Whatever buttons you have, when the button is pushed, we're assuming that generates a logic 1. Now, if your push buttons generate a 0 when they get pushed, you need to do something to make it work with this kind of circuit, or you need someone to design a different circuit where 1 means not pushed, 0 means pushed, and so on. But this is just the top level view. What goes in, what goes out, what do they mean? All right, and from there we typically make a truth table. So truth tables, technically you can put these things in the left on any order that you like, but they're almost always going to be in this order. And we'll talk later today about why they're in this order. This is how we count in binary. But the goal is to list all the possible combinations of all of the inputs. 3 inputs, all the different ways that those can be assigned ones and zeros. And for each of those, we're going to show what the output value is. All right, so that's our basic setup. So let's actually think about how we can build a circuit that would implement this locking system. And we're going to start off with this system being locked in all cases except one particular combination. If the person pushes all 3 buttons, I want the system to unlock. Alright, so we got 3 buttons A, B, C. You can try different combinations. You got to hold all 3 down. That's what unlocks the system. And now we'd like to write an equation in some terms of A, B, and C, which will be equal to 1 exactly when A is 1, B is 1, and C is 1. So any ideas what kind of logic we might want to use here? What kind of gate? How we might possibly do this?
Just an and on all 3 inputs.
Let's do an and. Right? If you listen to what I did when I described it, I said we want to unlock when A is 1 and B is 1 and C is 1. Right? So an AND gate is going to work really well. And remember, with an AND, we just put a little dot in between these things. So a dot means AND.
Could you just do ABC?
Or you could just do ABC. And it's just like multiplication, you know, if you write xy, we assume it means x times y. So if you write ABC, we assume there's an and in between them. All right, so here's the equation for our circuit. We've designed our first Engineering 250 circuit, right? This will unlock the system when A, B, and C are all 1. All right, well that worked out great because this is what AND gates do, right? But suppose we made this a little different. Suppose we wanted to have a slightly harder combination, and we wanted our system to unlock only in this case, where A is 1 and B is 1, but C is 0. All right, this is not actually any harder. Well, it's a little bit harder. So when we wanted to unlock here, we said we want A to be 1 and B to be 1 and C to be 1. In this row here, A is 1 and B is 1 and C is 0. Well, AND gates don't work with zeros, right? They only give you an output of 1 when all the inputs are 1. But if C is 0, that's the same thing as saying C is not 1. Because it's binary, everything's a 0 or a 1. If C is 0, then it's not a 1. And if C is not a 1, that can be reworded as not C is a 1. So this is how we're going to be able to write an equation. We're going to say we want to unlock when A is 1 and B is 1, and the negation of C, not C, is also 1. Because if C is 0, not C is 1. And so in this case, our unlock circuit is just this. And here, a little C with a bar on top means not C. So it's the inverse of C. All right, still with me? So if we unlock when A is 1 and B is 1 and the negation of C is 1, this is the truth table we've just realized.
I'm assuming. Oh, go ahead. No, you're good. Go for it.
I was just going to ask, there are different variations on writing C naught, correct?
Correct.
Like there's like a C apostrophe or like a C a line over and or stuff like that.
Yeah. So because we work with typewriters usually, and it's hard to put a bar on top of something. Sometimes you'll see C with an apostrophe. Sometimes you'll see C with a number sign. If you want to be really clear, you can say not C. But I'm going to suggest if you write something like this, put a little note or use parentheses to make it really clear. Because some people might write an apostrophe followed by a C. And so that raises the question, if you were to write A, B apostrophe C, is it A not B C, or is it A B not C? Right? And you have to know what the convention is. But if you throw in some parentheses, then it's pretty clear, yeah, you're trying to negate B. Same thing with a number sign. So yeah, there's lots of ways to do this. If you're writing out by hand, definitely put the bar on top, because that's absolutely clear.
Okay, sweet.
The other thing about bars, though, is you need to be really careful. If you wanted to do A bar ended with B bar, you can write it like this, but you can't write it like that. They're not the same thing. And, if you write really fast and you write kind of quick, you end up with that. Well, it's not clear if you meant that or that. So here again, parentheses can save the day. All right, cool. So here's our truth table for a different secret combination. ABC bar. All right, so only got one more step and then we're done, right? Suppose we want to have two combinations that unlock this. Suppose we still want, our original secret combination, but we want another combination that we can give to a friend. So we want either of these to unlock. Sorry, say again? Say again?
Devin, I don't think your mic's muted.
Oh, I think that was background noise. All right,
Yeah.
so we want to unlock when A is 1 and B is 1 and not C is 1, right? But we also want to unlock when A is 1 and B is 1 and C is 1. And we want to unlock when this happens or when this happens. So we really just need an or of those.
I mean, in this case, you could just drop C and not care about
And we
it.
could drop the C. We'll wait a few days to do that, but yes, you're absolutely right. All right, so with this approach right here, we can write an equation for any truth table in the world. Right, now they might be very long, cumbersome equations, but we can do it. Right, so here's an equation for this. If we wanted to add, another secret combination, say this combo right here, if we wanted that to also unlock it, all we have to do is know which expression should we write that will be 1 when A is 0 and B is 1 and C is 0. Well, this is an expression when A naught is equal to 1 and B is equal to 1 and C naught is equal to 1. And so if we OR with this, there's an equation for that truth table. So that's all it takes to write an equation from a truth table. And when we write an equation like this, in this form, this is called a sum of products. Abbreviated SOP. So this would be the SOP, or the sum of products equation, corresponding to this truth table. Remember, anding, since it looks like multiplication, we call that a product. Oring, since we use a plus sign and it almost works like addition, we call that a sum. And so this is a sum of, 3 products in this case. So this is an SOP equation for that. All right, good with this? This is mostly rehash of 120.
Yeah. We still use the apostrophe on our assignments.
I would prefer, if you're writing it, put a bar on top.
Okay.
Because it's less ambiguous and it's more standard. But if you have to type it, yeah, you can use an apostrophe. But be really clear, you know, if you mean like AB with a complement for the whole thing, you got to put AB in parentheses and then put the apostrophe after. All right, so this has nothing to do with combination locks, right? We can take any truth table for anything in the world and we can use this same method. And it doesn't matter what the function is, right? Anytime that we want a 1 in this row of our truth table, we're going to end up writing, you know, A bar, B, C bar, or X bar, Y, Z bar if the variable names were X, Y, and Z, and so on. And so we can think about this and work through it and come up with these equations. But once we've done that a few times, we can start shortcutting. So let me write out our standard left-hand side. And we can just make ourselves a table, right? If we want a 1 in this position, we're going to write A, B, C. If we want a 1 in this position, we're going to write A, B, C bar. What about in this position? If we wanted a 1 in this row, what would the combination of A, B, C bars be?
A naught, B, C naught.
A naught, or A, B naught, C.
Yeah, so
Sorry, I got it backwards.
okay, that's fine. A, B naught, C. And what about this one?
A, B naught, C naught.
All right. So we're starting to see a pattern here, right? If we have a 0, we put a bar over the variable. If we have a 1, we don't. So there's a 0, I'm going to write A bar. There's a pair of 1s, I'm just going to write BC. There's a 0, I'll put an A bar. A 1, I'll put B. A 0, I'll put C bar. And there's a pair of 0s and a 1, and here's all 3 zeros. I'll put bars over all 3. And now if someone gives me a truth table and I've got a 1, you know, here and here, I'm just going to do A bar B C bar or A bar B C. I'm just going to pull these terms out and put plus signs in between them. So these are sometimes called product terms. But we have a slightly fancier name for these. We actually call these min terms. The reason is unsatisfying. But we call them min terms. And you know, if we write our truth table in this order, right, where we list the combinations of A, B, C in this order, then the first min term is always going to be A bar, B bar, C bar. Or, you know, if this is PQR, it's going to be P bar, Q bar, R bar. And the last one is going to be PQR, or XYZ, or ABC, or frog, dog, banana, whatever we call our variables, right? They're going to be listed here, they're going to be listed here with bars on top. So, you know, we're engineers, we're lazy, right? That's why we go into engineering. That's why I went into engineering, right? Because I'm lazy, and engineering lets you be lazy. So we don't want to have to remember this. We don't want to have to write these things out, worry about the bars. So we make abbreviations. And the abbreviations are lowercase m with a subscript. And this lowercase m means, in this case, since our variables are A, B, and C, right? M7 is a shortcut for ABC. M3 is a shortcut for A bar BC. All right, which means if I go back to my equation, I could have, if I know the shortcut, just said my unlock is equal to, this is M01, M2, ORed with M6, ORed with M7. And as long as you know what the order of A, B, C are, this is exactly the same information as that.
Is that the same on, say there's 4 variables, is it different?
It's exactly the same thing for 4 variables, except we would have, 4 inputs, so we would have 16 combinations, and we'd have M0 through M15. But exactly the same concept.
Okay, that makes sense.
And this laziness thing is not a joke, right? It can go to extremes. Well, every equation that we write for a truth table is just going to be a bunch of these m's added up together, right? So unlock equals m2 plus m6 plus m7. Well, we can write that even more succinctly, and we can say this is just, and we use a summation symbol to mean sum. We can just say add up min terms 2, 6, and 7. And this has exactly the same information as all of that. But it's a whole lot easier to write. So this is called min-term form. This is called compact min-term form. And don't worry about this too much right now. This is about 2 homework assignments in the future before we really dig into this. But I'm just kind of giving you a initial view of it today. We're going to come back in a few weeks and we're going to revisit this, and we're going to find different ways to think about how to write an equation that corresponds to this truth table. We can do a dual thing, and instead of looking at the ones, we can look at the zeros. And we can say, let's write an equation that will be 0 in this case, and 0 in this case, and 0 in this case, and so on. And we'll end up with something called a product of sums representation, and we'll end up talking about max terms instead of min terms, and it's all a dual to what we do in 120. So just putting that out there for now. But let's just stick with equations, and let's dig a little deeper into this. All right, so we can write an equation from a truth table, and let's say, we've decided that unlock equals, I guess I'll stick to the original equations we had, so AB, C bar, or ABC, or A bar B, C bar. All right, so there's an equation. Once we have the equation, we can basically forget about the original word problem, which said, you are to design an unlocking system which responds to blah, 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 secret code, etc. We can forget about that. We can basically forget about the system diagram. This has everything that and we forget about the truth table. This has everything that we need to build a circuit. So we understand to some degree at least what these Boolean operations mean, right? A and B and C. Well, we know what an AND of 2 variables does, right? So if we have AB, we can describe the AND with a truth table. And so if we wanted to define the AND of 3 variables, Well, when we write A, B, C, it turns out we can think of that as A ANDed with B, C. Or we could think of it as A ANDed with B ANDed with C. And these are all the same thing. Okay, that's something called associativity. We'll talk about properties of these later. But we can think of an AND of 3 variables as, you know, just take 2 of them, AND them together, and then AND it with a third. Right? So if we think of this as A and B ANDed together, and then AND with C, well, let's make a column for A ANDed with B. And personally, when I write truth tables, I tend to break it up in groups of 4 just to make it easier for things to visually line up. So here's the 8 possibilities for A, B, and C. If I just fill in a column for A ANDed with B, right, 0 ANDed with 0, 0 ANDed with 1, 1 ANDed with 0, and 1 ANDed with 1. And now I can make a column for A, B ANDed with C. So I'm just going to take the AND of this column and that column. And, you know, 0 and 0, 1 and 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. But in this last spot, 1, 1, those AND together to a 1. So this is what we would think an AND of 3 variables would do. It would be zeros everywhere except when all 3 inputs are 1. But that's sort of a justification for why that's the case. All right, so this brings us into the idea of logic gates. So there are, you know, physical pieces of hardware out there that do these Boolean operations. And in, you know, in the STEM building and in our parts kit, we have these little devices that have places we can put in values for A, B, and C, and they have outputs. And we can read an output from there, and if the 3 inputs correspond to logic 1, the output will be a logic 1. Otherwise, the output will be a 0. And so we have symbols for representing these things. And so, for example, an AND of 2 inputs. Let me put this over here. We draw a symbol for an AND gate, which looks like this. And if this is A and B going in, this is A and B coming out. And if we want to do an OR operation, we draw an AND gate, but it's got a curved input. And when I draw OR gates, I put a plus sign in the middle. Just so that, you know, if my curved line gets a little less curved, or if my straight line starts to get a little less straight, it's clear this is an AND gate because there's a dot in the middle. This is an OR gate because there's a plus sign in the middle. And then my shape can get sloppy. So that's an AND, that's an OR. Do you remember what an inverter looks like, or a NOT gate?
Like a triangle?
Yep. So we're going to draw a triangle, and we're going to put a little circle on the end. And that's going to give us the inverse of the input. And this circle is kind of universal, right? The circle in logic diagrams basically means not. And so we can actually, so this is a NOT gate, or an inverter. But we can create this thing called a NAND, which is basically a NOT AND. So it means do an and then take the negation of the result, invert the result. And the symbol for a NAND gate is an AND gate with a little bubble on the end. So here's A and B, and what comes out is the NAND of A and B, and we represent the NAND as AB with a bar on top. And that's you know, literally what a NAND gate does. It does an and then a negation. And then a NOR, which is a not OR, is the same idea. It's an OR gate. And there's a little inverter on the output. And that's A or B bar. That's the NOR.
I have a question.
Sure.
So I understand the whole bar over both of them, but how would we do that on a computer with apostrophes?
I would say do it like that. Right, so that the apostrophe is on this combination thing, yeah.
Thank you.
Mm-hmm, you're welcome. All right, so there's some gates we can use to build circuit diagrams. And if we wanted an AND of 3 inputs, just use the same symbol, but throw an extra input outside. And the output is just ABC. And the same thing for ORs and NANDs and NORs. All right, so let's look at our unlock equation. So ABC bar, ABC, A bar, BC. And if we wanted to build a circuit for this, well, we have, you know, A and B. And we're going to AND these together. And we don't want to AND C, we want to AND the inverse of C. So let's take C and put it through an inverter. And there's our output ABC bar. And then we also want to AND A, B, and C. So I might take a wire here. And this is not what you want to do. All right, there's another AND gate. So that's ABC. And we also want A bar, B, C bar. So maybe we'll take A bar and put it through an inverter, and we'll take B, and we'll take C and put that through an inverter. And we'll AND that. And then we want to take the OR of these things. And so we'll make an OR gate, and there's our unlock. All right. And you can probably guess you don't want to turn in something like this for a lab circuit diagram, right? And if you're being paid to design a circuit, you probably don't want to hand this to your boss and say, here you go, I'm done, right? Because it's kind of sloppy, right? And it's really hard to follow, and it's really hard to know if there's a problem in here, if there's a mistake somewhere. And if you were to take this and try to actually build a circuit from it, you know, you've got wires crossing each other and all this kind of stuff. Okay? It works, but it's not ideal. So, so let's standardize this. So let's look at a technique we can use here. So this is a standardized way to draw a circuit from an equation. And you can use this in this class. You can use this in 270. You can use this like as a life skill. So let me write my equation up here at the top. So unlock equals ABC bar or ABC or A bar B C bar. All right, so here's what we're going to do. We're going to draw our inputs over here. And I'm going to draw a line coming down from each one. like that. And I'm also going to draw a connection from each input into an inverter. And I'm going to take those inverter outputs and run those down here. All right, and I can have, you know, as many inputs as I want, and this just gets expanded out. And now for each AND term, each product term that I want, I'm going to draw an AND gate.
Quick question.
Sure.
When you put those not symbols there, is it always a good idea to put something like that in there when you're building it, even though they may not be used?
So
Is that the point of it?
So ideally, you wouldn't have it if you're not going to use it. But if you don't think about it ahead of time, it's easier to just put them all in. If you look ahead and you know you don't have a B bar, you could leave that out. But I would say, you know, for practicing this technique, go ahead and just put them all in. Make it very mechanical. And that's going to work well in a few weeks when we start talking about programmable logic. Because we'll be working with something that looks just like this. Normally I just leave everything in, but I actually went ahead and I drew these in pencil because I happen to have my eraser handy, and I thought maybe I would get a little fancy with it. I don't know if I will or not. We'll see. Alright, so we're going to have an AND gate, and we want to generate A, B, C bar. Alright, well, all I'm going to do is I'm going to run some horizontal wires from here to those inputs that I want. In other words, I want an AND that takes A as one input. So I'm going to run a wire from here to A. And I'm going to put a little dot when I have two wires that are connected to each other. And then I also want to AND with B, so I'm going to run a wire over here to B. And I'll put a dot there. And I also want to AND with C bar. So I'll run a wire over here to C bar. And bingo, there's my output. And I'm just going to label this here to remind me this is ABC bar. And then I need another product term for the second term, and that's just ABC. So I'm just going to connect my inputs up to A, B, and C. And there's ABC. And then I have a third product term, A bar, B, C bar. And so I'll connect this input to A bar, this one to B, and this one to C bar. And there's my three product terms. Now all I have to do is OR those together to get my unlock signal. And so I'm going to take these and run them vertically into an OR gate. And the output of that is going to be unlock. And then if I want, you know, I can go over these in pen, you know, if I'm like being paid to do this or something. And then I can get fancy and take out those lines. You don't need to do this though on homework. Like I say, it's kind of nicer to keep everything in there. But you know, if I wanted like something I could like hang on my refrigerator or something, there you go. And that's, you know, a little bit neater circuit than what we had a moment ago. So you can use this to make a circuit diagram for any sum of products equation that you have. And it's a standardized technique. Alright, so I recommend using that when you're drawing circuit diagrams. And then if we were to take this and try to build it on a proto board, it's pretty easy to follow, right? Because things are kind of laid out consistently. All right. So questions. I lost a wire.
Earlier you mentioned that A bar or C bar isn't the same as I'll just say AC bar, right? Like the combined.
Mm-hmm.
Yes.
Yeah.
I mean, well, but in the case of this particular of an and, is that not the same? I mean, you're nodding the output. Oh, I get it. Oh my god. Okay. Yep.
Okay. Cool. But even though you got it, let's take a look at this, because you can always come back to a truth table, right? So if I do A and C, I get that. If I do A and C bar, I get that.
It's the inverse, yeah.
All right, now if I want to find what this is, I can make a column for A bar. I can make a column for C bar. And then if I AND those, that's a 1, 0, 0, 0. Right, so definitely different.
Yeah.
Anybody here remember De Morgan's theorem?
I don't think it was even mentioned in my class.
Okay, well,
Throwback to AP class.
cool. Yeah, we'll talk about De Morgan's theorem a little bit. Let me make some notes here. Yeah, we can do this right now. All right, cool. All right, so that's kind of the mechanical approach to taking an equation, turning it into a circuit. Okay, and we'll revisit this when we talk about programmable logic, because programmable logic basically takes advantage of this idea. Because if we draw, a half dozen circuits in this way, we're going to realize that, this part of our circuit always looks the same. It's a bunch of inputs with inverters and lines running vertically. And we always have a bunch of AND gates, and we have the outputs of the AND gates going into OR gates. And really the only thing that changes is, did we want a dot here or here? Did we want a dot here or there? Did we want a dot here or there? And by just moving around where these connections are, we can build circuits for totally different equations. And so there are devices out there called programmable devices that take advantage of that and let us basically build a piece of hardware by using software, by doing the things we do when we write a program. We would go into a piece of software, we'd say, I want an output which is equal to this, and it will build a piece of hardware for us that does it. Right? It'll rewire a chip internally to make it do this kind of thing and give us our unlock signal. So that's a few weeks down the road too, but preview of coming attractions. All right, so let's take a 5-minute break, and then we'll come back, and I want to look at things like this a little differently. I want to start looking at when things are the same as each other and when they're different, and take a peek at some rules related to changing equations around like this. And then I want to switch gears and start talking about representing numbers in this binary domain. And we're going to go beyond 120 and talk about not just integers, but fractions as well as negative numbers. So let's take a 5-minute break. We'll come back at 12:55, and we'll go into all of that. All right, cool. We're back. So, let's talk about, for a few minutes, some properties of these logical operations. And then I want to shift gears and talk about physical hardware. I'm curious. So, how many people here have had a lab class? I guess it would have been Engineering 120, CSE 120. Has anybody here done CSE 120 when we were face to face, where you actually went into the collaboratorium and used physical boards and stuff?
No, but I have breadboards and stuff here at my place.
Okay.
Me too.
Okay, cool.
I don't think I have any AND gates though.
Yeah.
Or gates.
Okay. All right. Yeah, and if you do 270 in the summer, that's going to be online too. But hopefully fall, we'll start some in-person classes again.
Chicken strips on that food court, man.
Yeah. All right. So you know, Boolean algebra, 1800s, right? This was developed George Boole. So this was a mathematical subject, and a lot of the stuff that we can do when we analyze logic gates and logical operations, kind of abstractly, a lot of that will carry over directly into actually designing and implementing circuits in hardware. And so let's just talk about a few of these identities or these properties of Boolean operations. The other reason for going through this is you're going to see these things again and again and again. They're going to pop up in lots of different forms. They've already popped up when you did KVL, KCL. You've seen some of this stuff, even if it looks different. When we do set theory, if you do discrete structures, CSE 215, this will pop up in set theory. This pops up in programming in a lot of different forms. So let's do a pass at this here. So an OR operation, A or B, it turns out is the same thing as B or A. And when we do an AND, A and B is the same thing as doing B and A. In other words, the order in which we do these operations does not make any difference. Right? If I switch C and A around, the AND is still going to be the same. So it's agnostic to the order of the inputs. And this is something called commutativity. If we do more than two inputs, we can do them in any order that we want. And that's associativity. And, you know, we're familiar with these things from working with numbers, right? 7 times 8 is the same as 8 times 7. If it wasn't, we'd be really surprised. 2 plus 3 plus 4 is the same as, 2 plus 3 with 4 added to it, or 2 added to 3 plus 4. And if that wasn't the case, we'd be really surprised, because when we add numbers together, sometimes we change the order, right? If we see a 7 and a 3, we add those together first because we get a 10. Or when we make change for a bill, right? So we're used to commutativity and associativity from dealing with numbers. Well, they also work for logical operations and an OR. That's not guaranteed, right? There's things we can describe where these do not work, where they're not commutative or associative. But for these operations, they are. And then there's nice things like this. If we take a variable a and we AND it with 1, we end up with a. Well, why is that? It just kind of happens. It may not be obvious from thinking about this, but if I take 0 and I AND it with 1, I get 0. If I take 1 and I AND it with 1, I get 1. All right? That's the proof or demonstration that anything ANDed with 1 will just give me back that anything. And similarly, if I take a variable a and I OR it with 0, I get back a. And that's also just kind of how the world works. If I take 0 and I OR it with, take 0 and OR it with 0, I get a 0. Take a 1 and OR it with 0, I get a 1. So a ORed with 0 is a ANDed with 1 is a. A ANDed with 0 is always 0, a ORed with a 1 is always 1. And we can go back to the truth tables and we can see that that's true. But if you think about it, this is saying, you know, I want an output of 1 if a is true, right? If a is 1 or if 1 is 1. Well, 1 is 1, right? So the OR is going to be 1. This should be equal to 1 if a is 1 and 0 is 1. Well, 0 is not 1, so this is equal to 0. A ANDed with a bar is 0. A ORed with a bar is 1. And you may have noticed or start noticing there's some kind of relationship here, right? I can take my 1s and 0s over here and I can replace them with 0s and 1s over here. And I change my ANDs into ORs, and I mostly get the same thing by doing these replacements. And so this gets into the idea of duals and dualism. And dualism is a whole topic in itself. It's a whole philosophy, actually. But it's the idea that as we develop topics in engineering, computer science, mathematics, we're going to encounter more and more things where we have a pair of operations, procedures, things, facts, rules, whatever, and they seem very similar to each other. And the example from 120 is KVL, KCL, right? And they feel very different. Most people are, you know, kind of okay with KVL, really, really hate KCL, right? About 10% feel the other way. They love KCL, KVL just seems weird. But they feel like very different things, but they're actually exactly the same thing. It's the exact same procedure if you replace loops with nodes, nodes with loops, currents with voltages, voltages with currents, right? You can make a transition, a translation from one to another, and they turn out to be exactly the same procedure. Okay? Similar thing happening here. ANDs and ORs are really kind of the same thing. It's a matter of how you look at it. Okay, so we call these things duals. And dualism is this idea that there's two of something when in fact there's only one thing, and there's just two different ways of looking at it. And that's a whole nother topic, and that's, you know, 30-some years of my research life. But we'll see this a lot, okay? Now there's this, right? AB with a bar on top. We've already said it's not the same as A bar ANDed with B bar. But it turns out it's the same as A bar ORed with B bar. And if we have A or B inverted, in other words a NOR, that's the same as A bar ANDed with B bar. And these are called De Morgan's theorems. So these are related to each other, but they're not the same, right? And the way to think of this is when you invert an AND, you can change that to inverting each of the individual inputs, but you have to change the AND to an OR. And that's another view of this dualism. All right, so in the text, there's a few pages of these kinds of things, and there's a whole lot more of these. And we'll come back to some of them from time to time. In particular, we'll use something called the adjacency theorem to help us simplify equations. But we'll get to that in a few weeks. All right, and you don't need to memorize these, right? You already know most of these. You already use most of these kind of implicitly, but they're in your text, and you should find that table of them and think about them and see if any of the identities in there are surprising, and play around with them. Always play around with this stuff, right? The more that you kind of work with these things, the more you'll internalize these concepts. All right, so let's make the leap to hardware. Because we've got truth tables, we've got equations, and we've got, circuit diagrams. And if we've got Tinkercad, right, that's kind of as far as we go. But Tinkercad, lets you do a kind of visual version of working with, physical hardware. And so the way we do this in a lab is, we have these physical devices, and we can put those into a protoboard. And there's connectivity here. I'm giving away the punchline for your experiment in lab 1, but right, all these holes are connected to each other. So if this pin of the chip is sitting in this hole, then this hole's connected to that pin, this hole's connected, this hole's connected, and so on. And so we can put a wire in here, and bingo, we got a connection to that pin. And we can connect that to a pin on another chip, and so on and so forth. And so we can build up circuits using protoboards. And you can get pretty complex with this. Right, so this was a circuit I was working on over winter break, and I actually know what each of these wires does, right? But it's the same idea. You have these boards, and you can put chips in there and run wires from hole to hole and connect these things together. And yeah, go ahead.
I was about to ask is that a Pico?
So this is an Arduino chip. It's an ATmega 328. This is actually an Arduino Mega, which wasn't connected to anything actually. But the whole thing is an old school Z80 microcomputer.
Just expanded?
Yeah. Yeah, all of this is actually support for it, and the Z80's over here. It's out of view. But yeah, it's just a lot of support circuitry. But it's the same concept as building an airplane landing system in 120, right? It's chips that are connected together through wires, and you can do pretty large scale things like that. So I don't have excellent lighting here. But when we use Tinkercad, or when we do this in the collaboratorium, right, we have protoboards, and we have chips, and we have wires, and we put them together like that. But there's other ways that that circuits are built in practice. So for example, this is a 7408. That's an AND gate, right? And the way this works is it's got 4 AND gates inside. So there's 3 legs. Here's another 3 legs. And then here's a connection that we make to ground. That goes to 0 volts. And then here's another 2 inputs. And those get ANDed and generated to an output. And here's another 2 inputs. And they get ANDed and generate an output. And then here's a connection to positive 5 volts. So 14 pins, 7 on each side. And there's a little notch, it's hard to see here, but there's a little notch right there, which tells me that's this side right here. So this is pin 1 over here. Well, that's great, but it's kind of big, right? It works really well for proto boards. But if we were building this for, you know, some other application, we might use a chip like this. And this is also a 7408. It's a quad dual input and gate. And it's 14 pins, right? But the pins are a lot smaller. And the pins, actually, they don't extend out beyond the bottom of the chip. Right? Now, the whole reason that you can put this into a proto board is because the legs extend beyond the bottom of the package. This, the legs end right there at the bottom where the package is. And this is called a surface mount device. And with a surface mount device, what you have is, so let me tag this. What you have is a circuit board, which has, you know, little pieces of metal on it, basically, and you place the chip on top of it, and you use solder, right, melted conductive metal, to basically connect each of these pins to one of these pads, and that's how you build up your circuit. Now, it's harder if you make a mistake or you want to change it. You have to remove the solder and so on and so forth. So it's not as convenient as a proto board, but it's a lot smaller, right? And we can continue that because there's chips that have, you know, pins on all 4 sides. So this is an 8-bit microcomputer. This is actually the processor you would find inside something like an Arduino. And it's got a total of 32 connections on it. But, you know, if this had 32 pins on it, it would be about this big. So here's a 32 leg chip. And you can go even smaller. And there's all kinds of different packages available, right? So I'll leave this one on for reference, right? So this is a device with 24 connections on it. And these little shiny dots around the side, those are like the legs on the chip. And when you mount this from the top, it looks like this. There's no metal exposed. And so that's a very small device. Here's a chip I was working with before class. And that's really hard to see. But that's actually a little tiny 6-lead device. And you can see there's 6 little legs coming off of it. Nice strobing effect there. And that's, you know, just a smaller form factor. So we can get all kinds of shapes and sizes for these devices. And, you know, if there's like a pandemic and we're locked down and you get bored, right, you can do things or find yourself doing things like, what happens if we take apart this chip and we look inside, right? What's actually happening inside here? Well, so I did this. I actually did this not because I was bored, because I had a chip and it wasn't working well, and I was really suspicious because I got it from Amazon. And I'm like, I think this is a bogus chip. So, you know, you get a Dremel. Dremels are great. And you just kind of like hack off the top of this. And it took me about 4 tries, 4 chips to do this. But eventually, you can get down to where you can expose the actual piece of circuitry that's inside this. And let me show you what that looks like. And this is just because, you know, everybody should see this. at some point. So there's the 7408 chip. There's the surface mount version. There's the AT-Mega chip. There's a little 28 lead flat pack. This is that little piece of silicon that I pulled out from the inside of this 7408. It was actually from a 74245. But it's the actual thing that does the electronics inside a chip. Most of this chip is empty space. It's large because we have, you know, 1/10 of an inch from one pin to another so that this will fit in a protoboard. But the actual chip itself is probably about, you know, from here to here. It's tiny. And so this 74245, this other chip like this that I took apart, this was what was inside. And if you blow that up, you can see there's a lot of stuff going on in there, right? These are wires and transistors and resistors. And you can take a close view of it, right? And this is what it looks like. And there's the part number, 245. And these points over here, these have really, really thin wires coming off of them that connect to those legs on the large chip and let you put it into a protoboard. So this is the stuff that we miss when we play with Tinkercad, right? But that's some of what goes on at the hardware level. Now,
How small would AND gates be in, say, like a GPU where it has, I don't know, I'd assume thousands or millions even?
yes, so I mean these are pretty small. If you take the cover off like an 8-bit microprocessor, it's still quite a bit smaller than the actual physical package. And you can find pictures of these online. But yeah, the scale is pretty shocking. Something like this is not a very cutting edge technology, right? It's a logic gate. It's probably using fabrication technology that's decades old. But you go inside like a modern 64-bit processor, and it's going to be, you know, a pretty large substrate, large enough that you could, you know, see it and hold it in your hand. But it's going to have a couple of billion transistors on it. So yeah, the scale is pretty mind-boggling. All right, so I drew a picture like this, right, that showed us what the 7408 looks like. I did that from memory, but in general, if you want to know what's going on inside a chip, right, how to use it and so on, you need to refer to the data sheet. So the data sheet is basically the Bible of a chip, and every chip has a data sheet. And so let's pull up Texas Instruments data sheet for the 74 LS08. And it's 23 pages long, right? My version was like 1 page. But here's, you know, a more detailed view of it. So here's the top view, right? This is like the picture that I drew. There's a little notch. There's the 14 pins. There's the numbering convention. Here's a description of it, right? 4 independent 2-input AND gates. Oh, these always start with marketing, right? Packet options include, and then the second statement, dependable Texas Instruments quality and reliability. Can't get away from marketing, right? Even a technical document. So there's a date. This was made in December 1983, so it's a little bit old. And this chip is known by many names: SN7408, 74LS08, 74S08, and also 54s. So there's a top view. Here's a different package. This is one of these 4-sided flat packs, and you can get it in that package. And here's a description of it, right? They're independent AND gates. The 54 series are what are called mil-spec. They work at a lower temperature, they work at a higher temperature, they're more resistant to vibration, they're more tolerant of voltage changes, and they cost more money. Right, so we always use 74 stuff, but you can get 54 stuff if you're in some kind of critical application. Here's the basic function table. This is a truth table. Each gate has 2 inputs AB and output Y. They use high and low instead of 1 and 0. So if both inputs are 1, the output's 1. If A is low and B is anything, the output's low, and vice versa. here's a logic symbol, which doesn't look like our logic symbols, but they claim it's in accordance with some standard. But you know, A and B go in. Here's an ampersand for and there's the output. And there's pin numbers on here. Here's the sort of standard logic diagram. And here's the equation, y equals a dot b, or they also wrote it as y equals a bar or b bar with a bar on top. Well, why did they do that? Well, that's a longer story. But if we think about this equation, De Morgan's theorem tells us that the not of an OR is the same thing as knotting each of the inputs and ANDing them. And an identity I didn't mention a little while ago is that if you negate something twice, you just get back the original thing. So A not knotted is just A, and B not knotted is just B. So this thing with all these bars and an OR is the same thing as just an AND. But they actually mention that in here, right? Why? Because sometimes we want to work with ORs and sometimes we want to work with ANDs. That's a whole nother subject. We don't have to worry about it too much. Alright, here's what's inside, right? Depending on whether you're getting the O8, the LS08, or the S08, here's a circuit diagram for what's inside a single AND gate. And these things are transistors, and these are resistors, and these are called diodes. And that's how this thing is wired together to act like an AND. To set it up so that if you put in two high inputs, the output is high. Right? Now, do we care about this? Probably not. But depending on what we're doing, yeah, we might need to know these kinds of details. And we might say, oh yeah, we need the 74SO8 because of this right here. Right? Alright, absolute maximum rating, so the highest you can run this is 7 volts. You put in more than 7 volts, the magic smoke escapes, and the chip doesn't work anymore. Operating temperature, so the 74 devices, 0 to 70 degrees Celsius. The mil-spec devices can go down to minus 55 and go all the way up to 125. That's beyond where water boils, and this chip will still keep working, which is pretty cool. And, you know, for an AND gate, we don't really care about anything except this. We know what an AND does, we need to know what pins are connected to what. But, you know, there's another 19 pages of information in here showing, you know, when we put in a combination of inputs and our output is supposed to be high, how high is it going to be? If we're supposed to put in a low, how low of a voltage do we need to put in? Remember, ideally, low means 0 volts, high means 5 volts. Well, what if I put 4 volts into an input? Is that going to be treated like a 1 or a 0? What if I put in 3 volts? What if I put in 2.5 volts? Well, the datasheet will tell you the answers to those. And in particular, it's telling me if I want to put an input voltage that's low, the most I can put in is 0.8 volts. And if I want to put in a voltage that's high, it has to be at least 2 volts. If I put in 2.5 volts, that's going to be a logic 1. If I put in something between 0.8 and 2, no idea. They're not making any promises. So there's information in here on how much power these chips use and so on and so forth. This is one we are going to care about in here, switching characteristics. So TPLH, this is the time it takes the AND gate to change its output from low to high. So suppose you're doing an AND of a 1 and a 0, the output's low. Suppose we change that 0 on the input to a 1. The output should change to a 1, but it doesn't happen right away. It takes time. How much time? That's what this column tells us right here. Typically 17.5 nanoseconds, maximum 27 nanoseconds.
If the max is 5.25 volts, would it be a bad idea to keep this in a circuit over time?
So recommended operating conditions mean you can leave it at 5.25 volts. And that should be perfectly safe. But maximum, right, where it says maximum input voltage is 7, you can't keep it at 7. It means if it gets a spike that goes up to 7, you'll probably be okay. But yeah, you should be able to operate it at 5 1/4 safely. And down to 4 3/4. And these, you know, when you make these specs, you have to know that it's not going to fail at 5 1/4. So you add some headroom, right? It'll probably work up to 5.5 volts just fine. It'll probably work down to 4.5 volts, maybe even down to 4. But there's wiggle room in there, right? All right, so these chips take time to do their thing, right? Switching from low to high. I'm looking at a different table now. Switching from low to high, right? 17.5 nanoseconds. Switching from high to low, only 12 nanoseconds. That's faster. Maximum of 19. This is going to be really important to us eventually, because we're going to build circuits that change, and we're going to need to know how things change relative to other things. And this difference, 27 to go from a 0 to a 1, 19 to go from 1 to a 0, that can be really significant. That can be the thing that makes, you know, rockets crash. So all of this stuff, you know, we're going to mostly ignore, but it's important to someone somewhere.
Well, and also the temperature that you're currently operating at is going to change the...
Right, right. So these numbers are given for exactly 5 volts, 25 Celsius, which is considered room temperature. But if you're running this in a higher temperature, it would probably switch faster. Lower temperature, I think it'll switch slower. All right, and then this particular data sheet from TI, right, they tell you all about the different ways you can order this. So each of these are slightly different numbers, right, and they correspond to different packages, different specifications, right, operating range, and so on and so forth. And, you know, it's more marketing, and there's some disclaimers in here about, you know, mistakes in here aren't our fault, and so on and so forth. And then, you know, if you're ordering it in this form that's surface mountable, they come on a reel. They come in these big plastic strips with little sprocket holes in here that you can plug into a machine that'll automatically build your circuit for you. But you need to know exactly how this is laid out, and, you know, what kind of box it comes in, and the exact dimensions of each of these packages. So how far apart is it from one of these notches to another? Or on our dip chip, the dual inline package, right? What's the angle of this leg coming down? It doesn't come straight down, right? This bottom part is not flat. It's tilted. It's a 10-degree angle, right? There's a picture. There's our dip chip. This is the one we put in the proto board, right? It's 1/10 of an inch from pin to pin, and on and on. There's the angle, right? Typically 15 degrees, which is why new chips are hard to get in your proto board sometimes. You have to bend the legs. So there's tons of information in here, right? And generally when you have a chip, you want the data sheet for it, okay? 23 pages of data sheet for an AND gate, right? When you get to Engineering 270, we'll be working with a chip called a PIC processor. It's a little 20-pin chip or 18-pin chip. The data sheet is over 300 pages long. And you'll get to know most of that data sheet by the end of the course. Right, it's effectively a second textbook for the course. So know about data sheets, take a look at some of them, and you can link to these through the ENGR250 website. There's a section for component specifications, and the data sheets for all the chips that we use in these classes are available there. All right, any other questions, comments about all of that?
This is not really about the content, but I'm curious why your wires were so unorganized.
Oh, on my that Z80 board?
Proto board, yeah.
Yeah, well, you know, that's my brain. I don't have a valid excuse.
I will say that I took a snapshot of it and sent it to like a couple of my IT friends, and they all about passed out.
Nice. Yeah. you know, so I was using mostly pre-made jumper wires, which, you know, come in whatever length they come in, so stuff sticks up in the air. And yeah, this developed organically over the space of about a month, and just kept adding more and more stuff. You know, it started with one board, which was actually down here, and two boards, and then I put them on a piece of wood, and eventually I grew out into two pieces of wood, screwed together with metal plates. And yeah, it just kind of developed like this. But you know, part of me wants to cut my wires to length and color code them, and part of me just wants to make a rat's nest. And those are kind of always at tension with each other, and that's kind of fun for me. But this eventually turned into this, right? A nice printed circuit board where basically all of those wires are inside this material, and you can kind of see these lines here. Those correspond to the wires. But yeah, you know, you start down a path, and if you don't start off with the intention of making it nice and neat, it just gets worse and worse. And it got worse than this by the time I was done. But it worked, which was even crazier.
Build now, polish later.
Yep, yeah, which means polish never. Yeah, there's probably contests out there for the worst rat's nest proto board, and this doesn't even come close. I actually worked with an engineer. This was for Naval Research Lab, and I would go visit him after hours, like 5 o'clock. I'd be getting ready to go home. I'd pop into his office, and number one, he smoked, right? And so his office was always this cloud of smoke. But he always had, you know, something like this, but just completely covered with wires. I mean, you couldn't even see like a proto board underneath. It was really, you know, it was literally like a rat's maze. And I'd be like, you know, so what you working on? And he's like, yeah, I've got a bit of a noise problem in my signal, but I think I found the problem. And he'd like stick a pair of tweezers through this massive wire, and he'd wiggle something on the oscilloscope. This signal would like totally clean up and would be a perfect sine wave. He'd be like, oh, I knew that was the problem. And he was just, yeah, he was otherworldly.
That's insane.
Yeah, so these are typically called rat's nests. All right. So let's talk about numbers and stuff. And when I write truth tables for equations, right, I'm always writing them the same way: 0, 0, 0, 1, 1, 0, 1, 1. Technically, you know, if I swap my rows around, it's still a valid truth table, but almost every truth table you see will be written in this order. And the reason is there's ways to convert, there's ways to take numbers and write them in binary. And what I'm basically doing is I'm writing consecutive numbers in binary in this left side of a truth table. So let's talk about how we represent numbers with binary. And again, this will start off with stuff you've done in 120, but we're going to move beyond that. So in plain old decimal, right, I can write down a number. Okay, have any of you ever seen this number before in your life?
It's max 32.
It's not. It's a good guess, though. It's a totally good guess. I'm guessing nobody has ever seen this number before. I've never seen this number before, right? It's a random number. But I'm willing to bet that every one of you knows everything you need to know about this number just from what I've written, right? For example, if I take this number and I also write the number this, you can tell me which of these two numbers is larger, right? It's this one, right? Why? Well, it's got more numbers. You could tell me how much larger by subtracting. You could even tell me what you get if you multiply these, even though none of you have ever seen this number before, right? That's kind of amazing. Well, why does that work? Because this is not a random representation of the number, right? This number means this number because we have a methodology for writing numbers in decimal. And our methodology is very, very simple and specific. This 2 represents 2 times 10 to the 0. It represents 2. It's the units place. This 9 is in what we call the tens place. It represents the number of tens in our number. This 8 is in what we call the hundreds place. It's the number of hundreds. So this number right here is 8 100s plus 9 tens plus 2 ones, 892. And we can keep doing that, and we can write any number that we can imagine, and we know what it means. Okay, so this is something called weighted positional notation. Now, do we have to use weighted positional notation to talk about numbers? No, we don't. I could say, you know, this is the number 4, and this is the number 7, and this is the number 3. And, you know, we could build our whole society around a collection of crazy-looking symbols that correspond to different numbers. And, you know, to some degree, the world would still work. But we don't do that. We have a methodology for writing down a collection of symbols, and that's all that these are. These are symbols to represent numbers. And so we use this weighted positional notation. This is the units, the tens, the hundreds, the thousands, the 10,000s, the millions, and so on and so forth. Okay? That's exactly what we do in binary, except that our positions have different weights. So when I write something like this, this is the 2 to the 0 place, the units. This is 2 to the 1, 2 to the 2, 2 to the 4, 2 to the 8. Sorry. 2 to the 3, 2 to the 4. Right? So this is 1, 2, 4, 8, 16. And so this number means 1 times 1, 0 times 2, 0 times 4, 0 times 8, 1 times 16. That's 1, 0, 0, 0, 16. Add them up. 17. Alright, so that's what's going on when we write binary. We convert between binary and decimal and so on. But because we're doing this, you know, not with a random assignment of bit patterns to numbers, but with this weighted positional notation, we can do things like add numbers together. And we can add them the same way that we add numbers, you know, that we learn in grade school. We can add them column by column. And so if I want to do 17 plus 5, well, here's what 17 looks like. Here's what 5 looks like. And it's exactly the same thing we learned in school. 1 plus 1, well, that's a 2, but 2 is not a thing, right? Just like 10 is not a digit, 2 is not a digit, right? First of all, 2 is actually written like this in binary. And so we write down that 0 and we carry the 1. And 1 plus 0 is 1. 0 and 1 is 1. 0 and 0 is 0. 1 and 0 is 1. And that turns out to be 17 plus 5. Right? This is 2 plus 4 plus 16. That's 22. That's 17 plus 5. So by using this weighted positional notation, we get to do arithmetic the same way that we're used to. And we can teach that to a computer, so that when we store our numbers in the computer's memory in this binary representation, we can write programs that'll add and subtract and multiply and divide. And they use the same things that we use when we learn how to do that with decimal numbers. We can also compare. I can look at these two numbers. I know immediately this number is bigger. Why? Because when I start from the left, the first time I hit a 1 is in this number on the top. So that's the bigger number. But this is not the only way to represent numbers in binary. We could do, for example, something called binary coded decimal. Or sometimes called BCD. And suppose I take the number 235. That's a decimal number. I'll put a little period at the end to mean base 10. Well, we could write that in binary and, you know, it would be a bunch of powers of 2 added together. But there's a different way we could write this in binary using BCD. BCD is very easy to do the conversion. What we do is we simply write each digit in binary. So the number 2 in binary looks like this. The number 3 in binary looks like this. The number 5 in binary looks like that. So we're really doing this. Well, there's 12 binary digits that correspond to the number 235. But it's not weighted positional notation. This is not, you know, 1 plus 4 plus 16 plus 32 plus 512. But it's a perfectly valid representation. So these decisions about how are we going to represent things using binary are somewhat arbitrary in the sense that we're not required to do it a certain way, but there's advantages to doing it certain ways. This has an advantage that it's really easy to write. And if someone gives me this number and says, what number is that? Well, all I got to do is break it up into groups of 4 and say that's a 2, that's a 3, that's a 5. I'm done. It's a whole lot quicker than taking my number and figuring out powers of 2 and adding them up. But if I write my numbers like this, I can't just do, you know, arithmetic the way that I'm used to doing. Alright, so there are other ways to do this, but we're mostly going to stick with this weighted positional notation. And so let's, yeah, we got about 10 minutes left. Let's look at converting decimal to binary. So suppose you have a number and you want to write it in binary. And I'm not sure how Jim does this in 120. There's a few different ways to do this. One is trial and error. One is by successive subtraction. Let me show you a very systematic way to convert a number from decimal to binary. So let's take a number like, I don't know, 59. And let's try to write that in binary. Okay, so here's an algorithm we can use. Take 59 divided by 2. Okay, I'm going to get 29 with a remainder of 1. I'm going to take that 29 and divide it by 2. I'm going to get 14 with a remainder of 1. I'm going to take 14 divided by 2. I'm going to get 7 with nothing left over. I'm going to take 7 divided by 2. I'm going to get 3 with 1 left over. Take 3 and divide it by 2. I'm going to get 1 with 1 left over. Take that 1 divided by 2. I'm going to get 0 with 1 left over. And then at this point, if I keep continuing this, I'm just going to keep getting 0 divided by 2 is 0 with a remainder of 0. So that'll go on forever. All right, now if I write down these remainders, there's my number in binary. And that always works. And there's no guesswork involved. There's no trying to figure out the largest power of 2 that's less than this and subtracting powers of 2 and all that. Just keep dividing by 2. Look at the remainders. The remainders form the bits of your number. All right. Have you seen? Do you do that in 120?
I've never seen it.
Okay.
I always like memorize the powers of 2 and how far below it is the next one. So like binary 64, or I mean, sorry, 2 to the just know the positions 1, 2, 4, 8.
Okay,
16,
cool.
32, so forth. And is it smaller or greater? And how many digits is it?
Cool. Okay. And yeah, that's usually how we're actually going to do this in practice. But if we wanted a computer, for example, to convert from decimal to binary, this is an algorithm we can use. The nice thing about this is it also works for fractions, or FR fractions. So suppose we want to represent something other than an integer. Suppose we want to represent the number 0.3125. All right, so let's start off with that. Let's multiply by 2, and we'll get 0.625. We're going to take the decimal part of it, multiply by 2, and we're going to get, I made my life hard here, 1.25. We're going to take the decimal part of it, multiply by 2, we get 0.50. Take the decimal part, multiply by 2, we get 1.00, and now we're going to keep repeating. And so on. Well, in this case, what we're going to do is we're going to take these things that came before the decimal point, and that's going to be our number in binary. Okay, so what does this mean? Well, it's exactly the same thing. It's weighted positional notation, but this is 2 to the minus 1, 2 to the minus 2, and I feel like I made a mistake somewhere. So this is the 0.5, the 0.25, the 0.125, the 0.0625, the 0.03125, and so on. And we just add up the corresponding powers of 2, negative powers in this case, where we have a 1. Yeah, I think I got it right. So 0.25 plus 0.0625. That's 0.3125. So 0.3125 in decimal could be written as 0.0101 in binary, and I'll put a little 2 there to indicate binary. And if I wanted to write, you know, a number that was a fraction but bigger than 1, like 59.3125, it would be 59 point, and then you write down the fractional part. 3125 is 0101 base 2. So now we can represent things that aren't whole numbers. Okay, but it's still weighted positional notation, right? 2 to the 2, 2 to the 1, 2 to the 0, 2 to the negative 1, negative 2, negative 3, negative 4. And to convert something bigger than 1, we can divide by 2 and look at the remainders. To convert something smaller than 1, we multiply by 2 and we look at the things to the left of the decimal point. And so this is the way that non-whole numbers can be represented in binary. And because it's weighted positional notation, again, we can add, subtract, multiply, divide, compare, and do all the other things we're used to doing. If I take two numbers like this and I just add them column by column, I'm guaranteed I'll get the correct binary result corresponding to the answer.
Is this why that in some computer languages, if you use something like a floating point number, there's an inaccuracy towards the end?
Mm-hmm.
Like if you get an endless repeating number or a non-terminating floating point number at the end, it's messed up, right?
Exactly.
We had that problem in my C class
I
earlier
was about to
today.
mention that, actually.
So here's a fun problem.
Figure out what the problem was.
Try to write 0.1 in binary. Right? Using this approach, instead of 0.3125, start off with 0.1 and try to write it out in binary and see what you get. That's a fun, ungraded problem to try for Tuesday. And we'll talk about that on Tuesday. And then we'll talk about negatives. And we'll see how we represent negative numbers in a way that lets us continue to do, you know, addition and subtraction the way that we're used to doing. All right, and then we'll switch gears and go back to looking at circuitry. We'll look at a little bit about resistors and switches and current and things like that, and that'll take us into Lab 2, which we'll go through on Tuesday. All right, we are out of time. If you have lab questions, I've still got office hours tomorrow morning, Monday morning, Tuesday morning, and Tuesday right before class. And then your lab is due Tuesday at the beginning of class at 12. So plenty of time to finish that up. That's all I got. Have a great day. Have a great weekend. I will see you next time.